But hey, let's continue. We left off writing down this algorithm without really explaining what's going on here. At least there are two important elements that we need to specify. Otherwise, this is just, weird notation. So we're gonna need to talk about this proposal probability Q and this acceptance probability A, or in the end, this parameter alpha, which is not related to the alpha from the first slide. There was also a model parameter called alpha, but this is just some number that I will write down now, and then we're gonna explain or understand it intuitively. So what should be the proposal probability? There's really only one condition, which is related to the first condition that we also wrote down before in this general scheme. It has to explore the whole state space. So in the transition probability, this is what actually lets us go somewhere. So this has to also reach every point eventually. And then this acceptance, so the acceptance probability alpha, this has to somehow encode the true distribution that we want to sample from, right? If we just accept every point or no point, then obviously we're not gonna draw samples from our desired distribution. So we have to put the information of this P of theta in this alpha. And how does it look like? In a very general setting, it's given like this expression. And you might recognize this, but we're going to try to understand these elements. So here is where the distribution appears, right? We have to put the true distribution here, otherwise nothing in this algorithm somehow relates to the sampling distribution. What is this here doing here? Before we talk about this, which you might already have some intuition here for, why do we need this ratio of the proposal distributions? Let's just look at an example. If the proposals are symmetric, so if for every two states this is true, then alpha is just the ratio of the P values, right? So if our proposal distribution has no bias in any one direction, and every proposal and also its opposite are equally likely, the proposal distribution doesn't appear in the alpha. And intuitively, you can kind of reverse this observation and say, we need to add this correction here if our proposal distribution is not symmetric. So if we get pushed in a certain direction with our proposals, we need to account for this in our acceptance rate. Otherwise, we can, sample from the wrong distribution. We're just going to get pushed in a certain direction by the proposals, but we're not going to, get actual samples from P, but we're going to get it from some weird combination of P and Q. Right, so this is easy, and it's now kind of, how do we interpret this acceptance, right? In the equilibrium example that you talked about last week, you had some intuition for this, I think. Do you remember what this ratio was in the end? I'm just going to squeeze this in here because it's just kind of a side note. So this alpha still continuing from down here. or what is the, let's say, the nice property of this expression when you think back to the start of the lecture? What was the initial problem that we had with calculating expectation values and integrals? There was one thing that we cannot really calculate, and in this alpha it doesn't appear. That's the nice thing. And that's the normalization of the probability. So this is the same even if you add, I don't know, some constant. Which would be the normalization or the evidence that we had before, and in statistical physics this is the partition sum that you just cannot calculate realistically, right? It's a object that contains many different contributions, combinatorically, many usually. So it doesn't matter what the value of this is, it just drops out in the end. So we started by saying the normalization actually matters for the expectation values. We cannot just ignore it. We're not just maximizing, but we found the algorithm that in the end doesn't care about it again. So that's pretty nice. So here the normalization also doesn't appear. That's the second observation. No matter if you have this term as well. Okay. And now I kind of want to get to the interesting part, so let's just look at two examples. Yes, so I'm not going to write it down, but you can now also write down the full transition probability to go from one state to the next state in this Markov chain, right? It would be a kind of combination of either you propose a state and you accept it, or you proposed some other state and rejected it, right? So there are these two cases. And you can write down the probability of a transition, not just a proposal, but the full transition. And then you can show that this Markov chain actually has the distribution P as its stationary distribution. It has it obeys detailed balance. Yes?
Do we also have to check that the process is reversible to make sure that it actually obeys the detailed balance condition? I think
that's a good question. Yes. Yeah, so reversibility does appear in these conditions to show that a state or a chain has a stationary detailed balance state.
Because we already have the irreducibility, we made that sure, but the other things are missing.
The thing is, so if you have this process and you write down the transition probability, then you can do this as a homework exercise actually. You can show that P of theta is a detailed balance distribution, and because it's unique and it always has to converge to this distribution, I think finding one is enough if the process is irreversible, but I'm not 100% sure now. Yeah, I would have to check.
Because if we don't have any further knowledge, just from what we had in the lecture now, we know that we need irreducibility to have a unique steady state, and we need reversibility to have the detailed balance condition. I think this acceptance ratio is based on the detailed balance.
Right.
So that's what we know now. We have to make sure this is a reversible.
Yeah, so what I'm saying is you can show that detailed balance is true with the distribution that I'm telling you, which implies then that it's reversible. Detailed balance is equivalent to reversibility of the transitions. That's what I'm claiming. So maybe we can put this as a homework or not. I'm not sure what the plan is. But let me show you some examples, because so far it's very abstract, and I would like to get to this very cool technique in my opinion, and then show you some pictures of that. But you're right, so maybe there's one format criteria missing here. I'm not 100% sure. Right. So
if you have a symmetric cube in this case, and if you use this Kolmogorov loop criterion, then if you go like up in energy or like up in log probability, this way and you come down, you only multiply once, and if you go the other way around, it exactly adds up to the same. So I think, at least if the Q is symmetric,
Yes.
then I think it's more or less easy to check that it's reversible.
I think that's true, but it doesn't have to be symmetric for this to work.
It doesn't, yeah,
And for this to
replicate, I think
converge,
that's the way-
yes. Yeah. So I'm going to show you also an example of not symmetric transition rates. Let's start with an easy one. So these are kind of examples now, and you also saw this more or less already in the last lecture. So it's something like a random walk in state space. But I will put it in quotes because the proposals are a random walk, but of course the full Markov chain is not a random walk. So, and this is usually called Metropolis-Hastings algorithm or method. So we're going to choose for our hue a normal distribution. I don't know, this is how many people write this. So normal distribution of our new proposal with mean, the old value, and some variance that you have to choose. Right? Or is it not squared, whatever. So you have to choose some step size, if you will. And then what you're going to do is you're just going to perform a random walk in state space, and I'm going to show you some animation in a moment. And then you apply this criterion of accepting or not accepting your proposals. So the alpha is just what we had over there. What's nice about this is it's very easy to implement and very efficient in the sense that you can generate many steps in a short time. What's not so nice is again, kind of in high dimensions, it might need very long to actually converge. And also this I'm gonna try to show you on an explicit example. For now, just take it for granted. That has to do with what we also talked about already, that in high dimensions you have a small volume that you're interested in, but there are just so many directions your random walk will go to. If you go in every direction with the same probability, the chances are very high that you're going to step in the direction where the probability decreases. And if it decreases, then your alpha probability is very low, and you're going to most likely reject the step. That's the very basic intuition behind this. Yeah, so you can basically get stuck in some corners of your state space. And it just takes very long to get out of there, but eventually, of course, you will get out. If you let it run infinitely long, it's fine. But you can see that, choosing the step size and, the shape of the distribution, these two things that create some trade-off. So on the one hand, you want large steps, right? So a high variance of your random walk, so you explore the state very fast. But the problem is large steps in these high dimensions tend to cause low acceptance rates. Or probabilities, yeah. And vice versa. So if you make too small steps, you're going to stay too long in one corner, and you need very long to transition out of there. Just as a very high level example, consider a distribution that looks like this, just in one dimension. Right? If your steps are very large, you're often going to step away from the high probability area to very low probability regions, which won't get accepted most likely. And if it too small with the step size, you're going to always stay in one of these regions with high probability, and it's very unlikely that you're ever going to get out of them. So your transition rate somehow needs to be adjusted to the problem. That's already something that we can observe here. That's usually the case. It's very rare that there's one optimal choice for proposals that fits every problem. Yes. But what I also want to highlight here is there are actually methods that can generate proposals in a smart way. You might still have to tune them, but you can create the proposals already such that they will almost surely be accepted, right? In this way, you can save a little bit of effort and don't have to create so many samples that will get rejected in the end. But try to find a way to stay in the high probability region, but still make large jumps. This is sort of the ingenious idea of the other method that I want to talk about, not only this random walk, but the second type, or the main method that I wanted to talk about in this lecture, actually. And that's called Hamiltonian Monte Carlo, very often. And at the start, it might seem a little bit far-fetched, but the more you kind of think about it, the more you can hopefully appreciate that it makes a lot of sense that it's very often, not always, but very often more efficient than just a random walk. Okay? So what's the intuition behind this? Very short recap. In the easy model, or any kind of equilibrium model, that's what you did last lecture. You had your acceptance rate, or you had your probability distribution of your state. Let's say these are some strings. That this is given by 1 over z e to the minus beta, and then here the total energy of the system, right? In this particular alteration. So you know this from physics. This is some argument about the canonical distribution of your states at a certain temperature. How likely are you going to find this state? And people started, using these Metropolis methods to find a way to get samples from this, to measure things like the magnetization. And the alpha, if you use the Metropolis-Hastings method, is then just something like e to the minus beta and then the difference in energy. So that's what we already heard before. You can think about probability of a state, something somewhat of an inverse of the energy of the state, right? High probability, low energy. And if you make a step and it increases the energy, the more it increases it, the more unlikely such a step is. You can think of particles, hitting the wall of your container that transfers some momentum, but at a certain temperature, there is a certain distribution of momentum of your particles on the wall. So it's very unlikely that a very high momentum gets transferred, and you can go to an unlikely state. And it's very likely that, the energy just decreases over time. This is the whole intuition behind this sampling method. And now we're going to turn this around. Okay? This is the basic idea. So the whole intuition is going to be turned around. We're not saying that energy is something that's real, that exists, and we're going to look at what does this mean for the probabilities. We're going to say that probability is what we're interested in. Our P of theta from the start, our Bayesian posterior, and we're just going to write it in the same way. like so, and of course we cannot just choose any h. H is exactly minus log of p of theta, right? And now nothing happened. I just wrote p in a very complicated way. I said e to the log is just the thing itself, and this constant in front of it is just the unknown normalization that I didn't know before, right? Because we don't know the normalization here, that means there is some unknown factor in front of everything that, that we're not interested in the end. It's just on the stator. But I just want to formally make this look the same as this. For two reasons. One is, you can appreciate you don't need any equilibrium physics to argue why the sampling methods work. And you can also just call this energy without real meaning. It's not an energy at all. It's just the law of your probability distribution with a minus. But you can use the same reasoning to imagine the sampling process. You have a landscape of energy, and you're rolling or you're running around in this landscape. And if you step uphill, that's unlikely or more unlikely than stepping downhill. This way you're going to reach the regions of high probability or low energy. Okay? And now let's take this even further, this analogy. And this falls out of the sky a little bit. But there are also good reasons. Maybe at the end, if we have time to talk more about the high-level moderation, why does it make sense? We can do that. But in the end, people tried it, and it turned out it works very well. This is the practical explanation, in my opinion. But of course, you can think about why this also makes sense on a kind of more abstract level. So the Hamiltonian in Hamiltonian Monte Carlo is there because we can create some analogy to Hamiltonian physics, where we have a Hamiltonian that doesn't only depend on the position, but also on some momenta, right? And calling them V and not P just because everything is already called P and I don't want to make this very confusing. So that's why this is the momentum in the Hamiltonian mechanic sense. And this usually has two terms, the kinetic energy and the potential energy. And just for this purpose, we can choose what they should be because we're making up all of this anyway. This is not a real physical system with a real energy. So I would just choose that this is our standard choice. Well, actually, let's call it M. This is the standard quadratic kinetic energy just for multidimensional systems, right? This is the vector product with some mass matrix in the middle. And this is going to be the potential energy of our system, and I want to use the same intuition that we had before, so I'm just going to take minus log p of theta for our potential landscape. And in this landscape, we're now putting a particle and consider its dynamics even just regular classical physics with a kinetic energy. Okay? I just made this up. This is not, it doesn't have to be like this, and in the end, this is not a real energy, but we can just write it down. So now we're looking to sample suddenly from a different space, right? This has now two variables somehow. So we're not actually sampling only from here theta, but from here theta and momentum, which we're going to still write as, something e to the minus Hamiltonian, which is given by this. But what this really is a normal distribution for the velocities, right? And then our regular v of theta that we had before, up to some normalization constants. So if you want to think about it differently, not just in the physics way that, you add a particle in this landscape and you let it roll around, what we're doing is we're introducing a second random variable, and we're basically squaring the size of our state space, because for every parameter we're introducing its conjugated momentum. But we're doing it in such a way that this new parameter has it as its distribution just a normal distribution, or Gaussian. Because, as you can tell, the Gaussian distribution is exactly the kinetic energy term in this way of writing it down, right? If you write down e to the minus energy, the kinetic energy term is the Gaussian distribution function. So there are two ways of looking at this in a certain sense. But this looks more complicated. Now we have to sample from a very even higher dimensional space, right? We had 8 parameters, now we have 16. So how does this help us in any way, you might ask? But if we look at the proposals and then the corresponding acceptance rate, you can see why it actually is more efficient in many cases, not in all cases. So what are the proposals? This is what we have to specify always, right? If we introduce a new MCMC method, we need to say how are we going to propose new steps. And there are 2 steps to this. One is we're going to draw a random momentum. Let's call it v tilde. Okay, sorry. This is our hue of v prime, theta, and v. Right. So we always have 2 variables now in our height, or 2 n variables. So first we draw a random momentum at our current position that we're going to call v tilde. And because the probability for the whole process is just a product of the theta probability and the Gaussian distribution, this is just going to be like drawing from the Gaussian distribution, right? And this is easy. We know how to draw a random number from a Gaussian distribution. The second step is the tricky one. We're going to evolve the system, so our initial position and this new random momentum, we're going to evolve it to some new place that, how am I going to call this? Yeah. Theta star and V star, and kind of running out of symbols now because they are not yet the final, oh actually they are, okay, sorry, I'm jumping ahead of my notes here. So these are now the final proposals, okay? So we're gonna evolve our initial positions with Hamiltonian dynamics. That's the whole point of writing down this. And I need a new piece of chalk. And you all notice that just, the evolution of this Hamiltonian system is just using the ordinary differential equations. Okay? So you are at your current location, you're drawing a random momentum in any direction and a random magnitude according to the Gaussian distribution. And then you just let the ball roll in this direction for a certain time fixed time t. And then your acceptance is the usual thing that we always have. And then gonna write down already the result, and then we can convince ourselves that this is actually true. Hamiltonian of theta prime v prime minus, Hamiltonian of theta. Like this. This will be the acceptance rate in the end. Do you notice anything weird about this?
Will this always be 1 because we have dynamics which conserves energy on the trajectory?
So, a very good question. Wouldn't it always be 1? Because Hamiltonian dynamics conserves energy. The Hamiltonian is the total energy. So if we take this ratio of the previous and the new position, the energy shouldn't have changed. And in fact, that's the whole point. So this is almost 1. And why it's almost 1 we're going to see in a moment. That's because of numerics, and nothing is always exact here. But it's almost 1, and very close to 1 usually. So in fact, almost every step in this scheme gets accepted. That's very different to the random walk situation, where depending on our step size, and any steps get rejected, and it doesn't really work. It can still happen here. So if you choose your mass of your particle in a bad way, let's say if you make it very heavy, then of course it cannot roll very far. If you make it too light, it's going to roll off to weird places. But still, the basic idea is that you're going to create steps that will almost always be accepted. That's one reason why this is so much more efficient. Although, of course, at the same time, this time evolution is more demanding than just drawing one random number, right? So this proposes that there's a lot more effort now in the Hamiltonian Monte Carlo compared to the random walk, but we almost always accept our steps. So it turns out in many real applications that this favors the Hamiltonian Monte Carlo in the end. So the trade-off is more on the side of this is worth it. This is worth going through the effort of doing all the time evolution here. Okay, let's.
So the only random thing is setting the momentum. We trigger.
Basically, yes. The only random step here, or the only kind of random number that we have to draw, is the new momentum at every step. And then, of course, checking if we accept this step or not. So we always have to ask, okay, yes or no, accepting or not. This is the second random number, but compared to before, it's also 2 random numbers. New momentum and then accepting. But why, so the last thing I want to kind of show you on the board before I show you some visualizations is, why is this true? So I made a huge step now. We wrote down alpha is this in the general case. So the ratio of the probabilities, which is exactly this, almost. And then the ratio of the proposals, but I didn't write down the proposal really in a closed form. And you cannot easily check if this is reversible or not, right? At least I couldn't when I tried. Because it has these 2 different steps, and it's kind of tricky to see this. So this, we're going to have to verify that this is really true and not just something that I write down to trick you. So in the end, I'm basically asking, why can I just look at the probabilities? Why is alpha just the ratio of, theta and v and why is the here suddenly? And we can just look at both steps individually of our proposal. That's really the the key message here. So step 1 is we're going to propose our new momentum, and this proposal that takes us from our Q at the theta at the previous iteration and V at the previous iteration minus 1. Sorry. Just the new momentum, we can consider this as a step in itself in our Markov chain. And this step has acceptance probability 1 always. So you can show for this one that, so alpha 1 for the first step is always 1 exactly. The reason is we're directly sampling from the correct distribution over all the momenta, which we can because it's just a Gaussian. You can also just write it down in one line, but I'm going to skip this in the interest of time. You're going to see that the proposal for the new momentum and the old momentum, they will exactly cancel the distribution in the alpha, right? So it's not symmetric. Certainly, the proposal of V tilde and the previous V are not the same, but they exactly cancel the true distribution. So alpha is always 1 here. And why is alpha in the second step exactly what we wrote down there? So now we go from I minus 1 and V tilde to our proposal prime and V prime under Hamiltonian dynamics. And this is what you just said, basically. We cannot easily write down the expression for the Q probabilities, but we know that Q of proposing this, given this, is almost, and leave some space here, maybe before the symbols, is almost symmetric. And why almost? Here, just have to be careful with the order now. If you think about it, what I'm trying to say is we are at this position, we're going to evolve forward in time and end up here. What I would like to say is that doing the same, starting here and evolving forward in time, ends up here, which is not true if you think about it, right? You have one trajectory, and following it, and then following it further doesn't take you back to the original place. What you have to do is you have to reverse the momentum at the end of your step. So here, and here I have to put a minus actually. And depending on how you want to look at it also here. So we had to modify the algorithm slightly by saying propose a random momentum, evolve in time, and then when you arrive at the new place, just turn around the momentum that you have. Because then doing the same thing, evolving forward in time and turning around the momentum, it leaves the transition probabilities kind of the same, right? It turns out that this doesn't matter in practice because at the every step you choose a new momentum anyway, so you're not going to hit this value. So that's why it doesn't matter for the implementation over there. It's still correct. But to show that it actually is the right acceptance probability, this alpha, you need to kind of formally introduce this sign flip in the momentum here. So evolve a trajectory forward, flip the momentum, and then you get the same probability that forward evolution and flipping the momentum is again the initial state. Okay? And that's it. So if you know that this is true, then you know that alpha is just the ratio of the probabilities. Yeah, so from this it follows that alpha is just the probability of the new proposal divided by, this was the previous one, and the one that we have drawn. And along this trajectory, the energy should stay almost constant. The reason why it's not exactly constant is you have to numerically solve these equations and integrate forward in time. And that means, in practice, you have slight deviations from constant energy. But it doesn't destroy the whole algorithm because you can just reject the samplers with the right probability, right? All you need, so what you definitely need is this line down here. You need to use a method for integration that exactly reverses the path if you turn around the momentum. And to do that, I'm just going to write it down, and we don't have time to talk about this, but you need something called symplectic integrators. It turns out for Hamiltonian dynamics, they have very good properties, which is that this is true. If you turn around the integrator and reverse the momentum, it's just going to trace back the same path that it took forward. But this comes at the cost of not having exact kind of energy conservation. But this is fine because it's just a proposal, and we can reject the proposal. If the energy deviated too much, then we have the right probability with which to keep it. So to summarize, and now I'm going to show you pictures, this method is in principle such that you always accept every step. So it's very efficient, and because you can travel quite far in your state space, if you follow the trajectory of your dynamics, you can explore the space in a very short real time, right? This is something that you cannot easily prove, but you can use your physics intuition basically to convince yourself of this. And to show you two examples, there are two very nice websites. So I put the link here, and you can also get the slides at the end, with nice animations of this. And I'm just going to open them and show you real quick. There's this website. It's a blog of Alex Roshnikov, I guess. And there are nice illustrations of everything that we just talked about. And first, this idea that the probability distribution on the left side could be anything, right? We're just going to imagine that this defines a potential landscape, potential energy landscape. If you take the log and turn it around, then it turns into this funky energy landscape here on the right. Okay? And then we can compare these two methods that we looked at. So one is just a random walk, and let's let it take a simpler energy landscape. So this is like the maximum head potential that you probably also know from other contexts, and it's hard to see here in the projector, but these are all the steps that the algorithm is taking. And you can see this point zooming around in this maximum head potential, and it's showing the herd location in the chain. And the whole collection of the green dots shows you the whole micro chain in the end. These are the samplers that you generate. What you can tell, now it's stopped, I think it runs for a certain number of iterations. In the simple random walk, it's a little bit random, obviously, that very often you will notice that there is a little bit of a high density of your points in one region, although you should sample everything equally lightly, right? And if you run it long enough, you will cover everything. But you can tell, hopefully, because it's kind of hard to see on the screen, you can tell that it's a little bit denser in some regions on the right here than on the left. Comparing this to the Hamiltonian Monte Carlo, here you can see how it works, hopefully. So you start somewhere, you take a random direction of momentum, and then you can see in red the trajectory of your particle in this landscape. In 2 dimensions, you can still nicely visualize this. It's really like the ball rolling around there, basically. And you can see it does some proposals, and ends up at a new position which can be quite far away from the initial position, right? Because you can slide along the low energy kind of valley in your distribution. And if you let this run for a while and just speed up the process, you should hopefully notice that it's a more even distribution, right? So in the same physical time, you can more effectively sample homogeneously. And another way how to see that this is very efficient is if you look at the rejected samples, which you can also select here. And I don't know if you notice any difference, but I don't at the moment. So there are almost no rejected samples, right? Otherwise, they would show up in red. And now compare this to the microchain, I did the random walk. You can tell in the region of high density, there are also many red points that suddenly appear, which were all the ones that we proposed but then rejected. So we had to stay at the same position in our chain. And that makes sense because if you are here, then it's very likely that you make a proposal uphill that it's going to be rejected. In the Hamilton evolution method, this almost never happens because even if you're uphill, you're staying on same energy levels in your phase space, right? And what you see in the end is just the real space coordinates, but they're just projected down again from this phase space, and they also stay in the high probability region, okay? So all of this is very abstract, but with these visualizations, at least I found it nice to imagine this in some real examples. And there's a second website that I also put there where you can also, look at this process of proposing a random direction, time evolution forward in time, and then checking if you accept it or not. And you can also choose different distributions and different parameters. Yeah. So just play around with this and you hopefully get a better feeling of this. Why are we doing all this? This is really the last part now. Because we wanted to fit some data or some model to the data, right? We wanted to know what are the most likely parameters. And this is the result in the end. If you do this, I took this also from another website with a nice example. This is now the equations that we started with. The rabbits and the lynx, and one is eating the other and trying to survive. Here are two Markov chains, MCMC Markov chains, in the state space of all the parameters, and only showing 3 here, that the rest looks very similar. And you can then, for example, make a histogram out of that and say, oh, this is roughly the distribution of my parameters. And it's the full distribution. It's not just the maximum, like the most likely parameter. It's really, the most likely one is probably somewhere here, but you also know the variance, and you could also tell if there are 2 peaks in the distribution or only 1, and all that kind of stuff. So that would allow you to go to your boss and say, oh, this is my expectation for the time evolution of this ecological system, and even put some, some kind of error bars, a confidence region around your prediction, which is really nice. Yes, and then hope you don't get fired in the future. Thank you.